world of roaring engines and the constant push for speed, there is a moment of silent, absolute necessity. The moment you need to stop. That critical transition from unchecked momentum to controlled safety hinges on a component that works in the shadows, enduring immense forces, transforming violent kinetic energy into dissipating heat thousands of times over its life. This is the story of the unsung hero of motorcycle performance and safety. The brake disc. Today, we venture inside the high-tech heart of modern manufacturing to unravel the precise, step-by-step journey of how a motorcycle brake disc is made, from a pile of raw, earthy materials to a gleaming, life-saving piece of engineered perfection. Our story begins not on the factory floor, but in the science of metallurgy. The soul of a brake disc is its material. For the vast majority of motorcycles, from daily commuters to apex hunting sport bikes, that material is a special high-carbon alloy of cast iron, often a grade known as G3000, or a high-silicon molybdenum iron. This is no ordinary iron, it is a carefully formulated recipe, a secret blend for many manufacturers, chosen for a sacred trio of properties: excellent thermal conductivity to carry heat away from the pad contact zone, inherent wear resistance for longevity, and most crucially, a high and consistent coefficient of friction to provide that predictable, firm bite every time the lever is pulled. The raw ingredients, piles of recycled steel scrap, primary pig iron, and precise alloys like ferrosilicon and ferromolybdenum, are gathered. Computer-controlled scales measure each component down to the gram, because consistency here is the foundation of safety. A single percentage point's deviation in carbon or silicon can alter the disc's very character under the extreme stress of braking. This meticulously weighed charge is then fed into the mouth of a roaring furnace. Within, temperatures skyrocket past 1,500 degrees Celsius, over 2,700 degrees Fahrenheit, reducing the solid metal into a bubbling, glowing crucible of liquid potential. This is a vat of pure molten transformation. Before the pour, a sample is taken, cooled, and analyzed by a spectrograph. This machine reads the elemental signature of the metal, confirming the chemistry is perfect, ensuring batch after batch will perform identically. While the metal reaches its liquid state, its future shape is being prepared in another part of the foundry. Here, automated molding machines create the disc's negative image from resin-bonded sand. The molds are formed in two halves, known as the cope and drag. The cavity inside is simple but definitive. It will form the disc as blank, the rough as-cast shape that holds the promise of the final product. The moment of truth arrives with a stream of incandescent orange metal. The furnace tilts, and the molten iron flows like luminous honey into the waiting sprue of the sand mold, filling every contour. As it solidifies, a key microscopic event occurs. The carbon within the iron forms into graphite flakes. This unique structure, inherent to gray iron, is what grants the material its excellent damping characteristics, its ability to absorb vibration, and its relative ease of machining later on. The filled molds travel down a cooling line, the fierce glow within them fading slowly from yellow to cherry red, and finally to a dull black over several hours. Once cool, they reach a shaking station. The molds vibrate violently, and the sand shell fractures and falls away, revealing the newborn brake disc castings within. They emerge as dark, rough objects, covered in a fine scale of oxidation, with lumps of excess metal. The gates and risers that fed the molten flow still attached. They bear only a faint primordial resemblance to the finished part. This is where the art of subtraction begins, where precision engineering sculpts the rough form into a geometrically perfect component. The castings, now called blanks, are transported to a clean, well-lit machining hall. The first stop is almost always a CNC lathe. A worker clamps a rough blank onto the lathe's chuck. With a command, the machine whirs to life. The blank begins to spin, and a sharp carbide cutting tool approaches. On contact, a tight continuous spiral of dark iron swarf peels away, and beneath it is revealed a smooth, shiny silver surface. This is the first act of creation through removal. The lathe's primary mission is to establish the disc's critical reference surfaces. It machines the mounting face, the precise surface that will bolt directly to the motorcycle's wheel hub, to an exacting flatness, often within a few hundredths of a millimeter. It also turns the outer diameter and begins to skim the two faces that will become the braking surfaces. This initial machining ensures the disc will run true, without axial or radial runout, wobble, when finally installed. From the lathe, the disc often travels to a multi-axis machining center. Here, the transformation becomes more intricate. Drill bits whirl to life, cutting the exact pattern of mounting bolt holes with robotic precision. End mills trace paths, machining the internal splines or the carrier screw holes, and carving any aesthetic contours or lightening pockets into the inner bell section of the disc. For high-performance floating discs, this stage is where the separate aluminum center carrier or hat is also machined, and the precise slots for the floating buttons or bobbins are cut. Now, we create the disc's signature, its functional fingerprint. Before any holes are added, many discs receive a pattern of shallow curved grooves machined into the friction surface. These are often called scrub lines or conditioning grooves. They are not merely decorative. Their purpose is to gently scuff the surface of new brake pads during the critical bedding and process, optimizing contact and heat transfer from the very first stop. They also serve as microscopic channels to clear away water, fine debris, and combat pad glazing. For performance and premium street applications, the next step defines the disc's appearance and advanced functionality, drilling and slotting. A plain machined disc is mounted onto a massive CNC-controlled drill press. Above it, a solid carbide drill bit, engineered for the task, rotates at high speed. In a shower of sparks and a sharp metallic whine, it plunges through the iron, emerging cleanly on the other side to create a perfect round hole. This process is repeated hundreds of times in a precise pattern across the entire friction ring. This is cross-drilling. The reasons are deeply engineered. First, heat dissipation. The holes massively increase the surface area of the disc, acting like tiny radiators to pull heat out of the mass and radiate it away into the passing air. Second, weight reduction. Removing this material lightens the unsprung weight and the rotating mass, improving suspension response and acceleration. Third, and vitally, they provide an escape route for gases. Under extreme heat, brake pads can release gases. If trapped between the pad and disc, these gases can create a lubricating layer, leading to a sudden loss of braking power known as gas fade. The holes vent these gases away, maintaining consistent pedal or lever feel. Alongside, or sometimes in place of holes, come slots. Using a thin grinding wheel or slitting saw, radial channels are cut from near the disc's inner radius out towards its edge. These slots perform a similar duty, but are particularly aggressive at scrubbing the pad surface clean, constantly wiping away glazing and maintaining a high-friction interface. They also play a strategic role in heat management by providing controlled paths for thermal expansion, helping to prevent the random, dangerous stress cracks that can form in a solid, overheated disc. Think of a disc under the immense thermal load of a racetrack or a long mountain descent. A solid disc can develop concentrated hotspots, leading to uneven pad transfer, warping, and fading performance. A drilled and slotted disc, by its very design, distributes that heat more evenly across its entire area. The holes and slots break up the heat patterns, preventing localized thermal crises and maintaining consistent, predictable stopping power. After the aggressive machining operations, the disc requires refinement and strengthening. It enters a shot-blasting cabinet. Inside, it is bombarded by millions of small, hard steel beads propelled at high pressure. The cacophonous ringing is the sound of transformation. This process does more than clean off residual scale. It work hardens the very surface of the metal, improving its wear resistance, and it creates a uniform, matte gray surface texture that is ideal for the next step. Most critically, it acts as a final inspection, as any hidden casting flaw or subsurface weakness will often be revealed by the blasting process. For many performance-oriented discs, The next step is a journey through a furnace for heat treatment. This is not to harden the iron like steel, but to anneal it, to stress relieve it. The discs are slowly heated to a specific temperature in a controlled atmosphere, held there to allow the internal atomic structure to relax, and then cooled at a prescribed rate. This meticulous thermal cycle releases the internal stresses locked into the metal from the violent cooling of casting and the pressures of machining. The result is a disc that is dimensionally stable, far less prone to warping under the wild thermal cycles of hard use, and one with a more uniform internal grain structure for ultimate durability and consistency. With its form finalized and its structure stabilized, the disc must now achieve perfect harmony. Every single brake disc undergoes dynamic balancing. Placed on a machine similar to a wheel balancer, the disc is spun at a high speed. Sensitive sensors detect the slightest imbalance, a heavy spot that would cause a minute but intolerable vibration at the wheel. A monitor displays a spike on a graph pinpointing the location of the excess mass. The solution is elegant and minimal. On the inner bell section, well away from any critical stress areas or friction surfaces, a small precision drill takes a shallow divot out of the metal, removing just a few grams of material. The disc is spun again. The graph now shows a smooth line. The imbalance is corrected. This ensures that at highway speeds, the rider feels only smooth rotation, not a dangerous handlebar-shaking tremor. The final stage is about protection and preservation. To defend against its eternal enemy, corrosion, the disc receives a protective coating. The discs, hanging from an overhead conveyor, descend into a bath of a special chemical solution, often a black oxide or zinc phosphate process. This is not a paint that sits on top. It is a conversion coating. The chemicals react with the iron itself, creating a new molecularly bonded layer of magnetite on the surface. The disc emerges with a deep, consistent, matte black finish. This coating is tough and corrosion-resistant, protecting the intricate drilled holes and the inner bell from rust, especially from road salts and weather. Every disc is also given a final, meticulous visual inspection by trained human eyes, looking for any imperfection in the machining, coating, or structure. Only the discs that pass every single test without compromise are allowed to proceed. These packages are stacked on pallets, ready for shipment to the assembly lines of major motorcycle manufacturers or to the warehouses of aftermarket performance parts distributors. So the next time you ride and you gently squeeze that brake lever, feeling the motorcycle slow with obedient, confident authority, it is a masterpiece of applied physics, materials science, and manufacturing rigor, all dedicated to one simple, vital purpose: to transform speed into safety, reliably, repeatedly, and without fanfare. It is a testament to the silent engineering that makes the freedom of the ride possible.